Oh, so right there down.
Is it injured?
Yes.
No. I thought you had a pattern.
Okay, let's start that. Yeah, because I want to give a very clear idea about the reciprocal space for everybody. I know a lot of people talk about reciprocal space, but they don't really have a pretty clear idea. So that's why I want to spend a little time doing that one. Remember last time we talked about, we just considered simple one-dimensional lattice, right? So they have, because we have periodic lattice, right? So then we are talking about any physical property at that lattice point. Suppose if it is at Fr, some say anything, charge density or anything. So now if I take some, remember, lattice translational vector, that in the two-dimensional, at one single dimension you can write as, say, it is t, is basically some integer number. So we say u times your a, right? A is the, so if you go from here, 1 times a is here, 2 times a is here, u is an integer, that's the impedance thing, right? This has to be integer, you cannot have half integers, right? So if it is a periodic function like this, we can always write this Fr as some Fourier sum, right? So if we have some n with some amplitude n, what is this exponential term should be? It should have 2 pi, what is the periodicity here? A, it should be 2 pi over A, right? So then you have to have your dimensions about this direction, say r or x, doesn't matter. Let's say x, that's fine. Then it should be x. Also, since you are summing over n, it should be n times your x, right? So that's how you write your property in terms of, because of this periodicity, that's the whole idea. Unless you have the periodicity, you cannot write that. So then if you write this one, so if I write this 2 pi or this one, I write as some different constant, say g, right? If you write that way, then I can sum this one over g instead of n, then I have say a g, e I, then this simply gx, right? Let's see. So now the whole idea of this periodicity is, if you take any point here, suppose if r plus some this t, right? They should be the same. So that's why I have write this Fr should be same as Fr plus t. So that's why we have the identical environment, right? So if you write this one, Fr I can write here as n a n e I g. Suppose this is x means r, right? Here equals. So Fr plus t means same thing. You replace r by r plus t. So that means you write this one as n a n e I g times now x becomes r plus t. So this is, you can write as, you know how to write, e I a plus b means e I a times e I b, right? So if we do write that way, you get a n e I g x or g r times e I g e, right? So now if these two sides should be equal, this side should be same as this side, then what is the only requirement? This has to be 1, right? If this is equal to this one, so because this part is exactly same, this part also exactly same, then this has to be 1. That's the only requirement. You should have EI GT equals 1. That's the requirement, right? In order to have that periodicity. That's the basic idea. So actually it's true in this case because T is U times A. If you plug in here, what do you get? So let's see what is EI GT. EI GT is what? EI G means 2 pi over n times A Then t means some constant times your a, right? The period state. So if you take this one, you can say, sorry, 2 times. So 2 pi over a times n, right? And here I write u times a. You can say a and a cancel. What you get? ei 2 pi times n times u. What is n? N is an integer. U is an integer. Then this whole thing would be integer. Then what you have is ei 2 pi times integer. What is this value? Anything 2 pi I times integer would be 1, right? So because it has to be even number. Right? So this is always 1. Please remember, later we need this relationship. So this is something everybody should know. ei 2 pi times any integer is always 1. This is very important. If it is odd, it becomes 0, right? Okay, so now we know this is for one-dimensional case. Now if you have a three-dimensional case, this situation should be this situation. ei gt equals 1, that is one dimension. In three-dimensional, this should be ei some three-dimensional vector times your three-dimensional, the translational vector should be 1. So now let's see how this one works. So we know t. In three dimension, how do we write t? Basis vectors a1, a2, a3, right? So then you write as, if you remember, if I say u1 times a1, u2 times a2, say u3 times a3. What are these a1, a2, a3? These are the basis vectors, right? So these, what are these u1, u2, u3? They have to be integers, and it cannot be fractions. Now, in order to get g, so g also some vector. So if I write g as some, say, different vector, suppose I write as some v1 times, say, different vector v1, v2 times v2 times v3 times v3. If I assume this a like this, right? So now what is the requirement? When you multiply the dot product, it should be an integer, right? 2 pi times integer, right? So how do you get that one? Then you have to easily adopt some constraint. I can easily write this one as something. This is what we need, right? So then what we'll see how these are related here. So I can easily write this a1 dot b1 equals, because it has to be eventually 2 pi, right? It has to be 2 pi. Also, I can say a2 times b2 also same, a3 times b3 also 2 pi. Anything other than that, a1, b2 or a1, b3 or a2, b3, any of these would be 0. That's it. If I have this relationship, typically we write this one as, I don't know whether you are familiar with something called the Kronecker delta. I can write ai dot bj equals 2 pi times delta ij. This means if I and j are equal, they are 2 pi. If they are different, it is 0. That's the Kronecker delta means, right? So that's the requirement we need. So any of these, so we can have even more, right? A2, B2 also, right? I think like this one. No, I think everything is here. Yeah. So only this equal things will be 2 pi times. Is this clear? Everybody should know this. Delta ij means delta ij equals 1 when I equals j. This is 0 when I is not equals to j. That's simple, right? So that's the requirement we need. So if that is the case, what we have? Now take this, what we need is this one, right? If I take dot product, what will happen? A1, B1, if you get now if I get T dot G, if you multiply, you get U1, V1 times A1, B1 means 2 pi. You get, I'll write 2 pi outside. Then you get U1, V1. Then how about these two? A1, B2 is 0. A1, B3, 0. So then if you take here, this one, 0, and you get these two, right? You get simply U2, B2. Same here, U3, B3. That's what you get, right? So now what are these? U1, V1. So we know these are all integers. Here also, we need to have V1, V2, V3 also, all integers. So if that is the case, so then what do I have here? EIGT means EIG dot T means EI G dot T means 2 pi times. What is this one? Simply integer, right? So that becomes 1. That's how we define this G vector. So when we define this G vector, we have these new sets of vectors, right? Actually, you can easily show this is because this is in real space, right? In a real lattice. So then this should be inverse because this cannot be. It should be unitless, right? So G should be inverse of T. That means T has the unit of length, right? So then G should have what? 1 over length, right? So or 2 pi over lambda length. 1 over length. Please remember, the G has the length of inverse length.
That's a wave number. Right?
Yeah, exactly same thing. Because if you remember in the wave equation, what we have, how do you write the wave equation? If you write any wave, say psi A E I K dot R, right? K is basically 2 pi over lambda. It's exactly same thing. Here we write this one as E I G dot T. You can see the relationship. This is T means like R, then G is more like K. So K is also reciprocal. We can say, that's why we call it this K space or G space or whatever. So these are all inverse. That's why we call it a reciprocal space. So they have 1 over length. 1 over length. Dimension. Actually it is 2 pi over distance, right? Here also we have this 2 pi coming here, 2 pi over distance. So we call this B1, these vectors, they are in the reciprocal space. So now requirement is this one, right? That's basically your requirement. But easily you can, that's the only requirement. But if you want to do it in for like 3-dimensional case, actually you can easily define that B1, B2 like this, right? Because we have, so if you write B1 as, because we need to have this 2 pi. So if I write this one as, because we have write in terms of write this one A1 dot So if you write this way, you automatically get that relationship. Why? If you take A1, if I take the dot product, this one by A1, what will happen? If I put A1 here, so this one and this one, same, right? So then they cancel, you get 2 pi. If you take if I multiply this one by say B1 by A2, then what happens? A2 and A2 becomes 0, right? So that means this is the right. Also you can see if you take this one, so that will exactly have the right dimension to get this 2 pi value. I'll show that one later. So that means you can also write B2 as 2 pi. This is in bottom we have the same thing, A2 plus A3. So then here you have B2 means A3 plus A2, A1, right? Because it's a cyclic, right? Then B3 you can write as same thing, 2 pi times A1 A2 plus A3. Then here you have to get 3, you have to have A1 plus A2, right? You can see how the cyclic way. This is exactly to get, the whole idea is because your T was this one, right? Some, say, U1, A1, U2, A2, U3, A3, right? That's why we have to write this G as some, this V1, V1, V2, V3, V3. So if you write this way, you satisfy this one, okay? So, but you can see this is easy to see it in 3 dimension, right? So you can see all this here. Yeah. 3, 1. So here everything is written here. So if that is the case, you satisfy this relationship, right? So, but next time I'm going to talk about something like 2-dimensional case, that you can use this relationship, but in 2 dimension you don't have the 3rd dimension, right? So in that case, only thing you have to do is use this relationship. So I'll show you how to do that one. So now we talked about this the reciprocal space. What does it really mean in reciprocal space? So that's why I want to give you, so all these things makes all the sense, right? You can see all these here. So let me show why this is related to reciprocal space. Suppose if I take my real space like this, okay? So now if this is a real space, now you can define all the planes, right? So in this case, but I take this as my x-axis and this is my y-axis. Please, sometimes in 2 dimension it doesn't matter, right? I'll take this as x-axis, this is as y-axis. So now if I draw some planes here, suppose that means I have, this is A1, right, in the x direction. This is A2. So now if I take these planes, can you tell me what are these planes? If I take this plane, you can say this is my x-axis is going to be intersected by 1, right? What is the y-axis? Infinity here. This is, I'm going to draw the Miller planes. So if I take this plane, suppose this is 0th one. If you take, this is x-axis, right? X-axis is going to be intersected at 1. Y-axis is parallel, right? So that means that is infinity, right? So then if you take the inverse, what do you get? 1 and 0. So these are 1, 0 plane. Because they just put the 0 also 3-dimensional. This is basically 1, 0 plane, right? Is that clear? So now if I draw vector 1 0 perpendicular to that plane. That's the important thing. That plane is 1 0 plane. Okay, so the vector I write normal to that plane, normal to 1 0 plane as some vector n 1 0. Is that clear? So n 1 0 means what? N 5. N 1 0 means this is a vector normal to that 1 0 plane. Is that clear? So now actually I can represent this 1 in the reciprocal space like 1 point here, because this is perpendicular to that plane, right, in this direction. So then if I come here, that is the plane represented by that vector here. So this means all these parallel planes I can represent by this 1 point in this plane. So this is actually reciprocal space. So this point I can write as 1 0. So this vector is simply, later we'll call it G10 or something. So same way I can draw this plane. What are these planes? You can see your, this is my x-axis, right? X-axis is parallel, that means it is infinity. Y-axis is going to be intersected at 1, right? This is y-axis. So that means this is 1. If you take the reciprocal 0, 1, these are 0, 1 planes. 0, 1 planes mean these are planes. I define the vector as n 0, 1. So n 0, 1 is perpendicular to 0, 1 planes. So that means I can plot that point as 0, 1, because that's in that direction, right? That is the point. That means all these planes I represent by 1 point. Actually this is in the reciprocal space. So like that you can draw all the planes. Suppose this plane. So half means only difference is this is going to be at half, right? So that means if you take this one, that becomes 2 0 planes, right? So that means this is basically, sorry, 0 2, yeah, because this is in the vertical plane. Yeah. This is 0 2 plane. You get 0 comes because it's half, right? So 0 2 plane means that is in this direction 0 2. Yep. Is that clear? So that means all these planes can be represented by this point in the reciprocal space. Now if you go here, how about these planes? You can see if you take this one is intersecting at 1 and 1, right? That means you have 1 1 plane. So if you take these other planes, normal to that plane is 1 1. So that is actually at this point. You can see all those planes I represent by this 1 point in the reciprocal space. That's basically the idea of that reciprocal space. All the parallel planes in the, like this, you can work out this one. So this is a space lattice. So then I define the reciprocal space. Each point in the reciprocal space represent these millions of planes by just 1 point in that direction. All these things. Now you can see how, if you want to do calculations in the real space, you have to consider all the planes, right? But if you want to do that calculation in the reciprocal space, you have to just consider one place. Now we know how to represent this plane just by this vector, right? Instead of doing this A1, A2, A3, now we have the reciprocal space represented by B1, B2, B3. See? Very simple idea. So now let me get back to what we used to remember. So that same notation, remember this is what I was talking about, a translation vector this way, and we said IGT is 1, right? So then we define T as this one. But I want to connect to what we started with. Remember we started our R vector as NMO, right? That's why we define. Then I'll write my reciprocal space vector here. I say G. Here I will call that vector G HKL. The reason is, remember we introduced the Miller indices HKL, right? So that we represented by HKL. So the same thing, this V1, V2, V3 means, in this case, we represent by HKL. That's how we define the Miller indices, right? Is that clear? Typically, we talk about our planes. So any plane I can represent by this GHKL. What does this mean? Can anybody say what GHKL means? HKL we know the plane, right? 110 or 200. GHKL means a vector normal to that plane, that's it. The same thing that I said, N10, that goes the vector perpendicular to that 10 plane. Just like that, GHKL means this is the vector normal to HKL plane. Please remember that one. This is the basic idea. GHKL vector means, this means vector normal to the plane HKL. Remember, this means plane, right? You have 200, something like that. But if I have this vector, this means that vector is perpendicular to this plane. Yeah.
The reciprocal space is always normal to the plane? Like
No, I'm talking about the reciprocal space. We are talking about some vector, right?
yes.
So another thing is, this is another, this is a good question. So real space, I need to identify some origin, 0, 0, right? Then I can go to any point here just by doing this integer m1, integer m2 plus integer 3 like that. Then suppose I have reciprocal space. So here we define A1, A2, A3, right? To A3. Now here we define what? B1, B2, B3, right? B1, B2, B3. Now reciprocal space I can go to any place by doing this H times B1, K times B2, L times B3. This vector is always perpendicular to HKL plane. Yeah, I'll show you how that one works here. So is this clear for everybody now? We have the real space translational vector, we have the reciprocal space vector. Important thing is you should know this vector is normal to the HKL plane. So then this B1, B2, B3 in 3 dimension we can write like that. So let's see how this is really. So this is also fine, right? Chronic delta relationship. So here, this is what I think your question. So suppose this is my 2-dimensional real space. Suppose this A1, A2, right? So this is, now I can draw all the planes. What is this plane? 1, 0 plane, right? Because this is intersecting at 1. What is this plane? 0, 1. This plane? 1, 1. This plane? 2, 1, right? Because half. Now you have all the planes, right? Now I want to go to reciprocal space. So again we have origin here. Now if I come here, this is my reciprocal space, I have origin. Now in the reciprocal space, these, suppose I have B1, B2. How do you calculate B1, B2? This one, that's all, right? If you do here, what is my B1, B2? I don't know, suppose B1 say, can be say B1x plus B1y, right? In the y direction, something, I don't know. But B2 also, I don't know that I can write as B2x plus B2 Y, like that. But only thing we know is, we know A1. What is A1? A1 is simply A times X, right? A1 is A times X. B is, A2 is this vector, right? That is A times Y. Now if you take this one, if you take this product, what happens? A1, B1 should be 2 pi, right? That means this one times this one plus this one times 0. That means this term becomes, so if I take this one, A dot B1, so what we have? A times B1x plus, there's nothing here, 0, right? 0 equals 2 pi, that means your B1x is what? 2 pi over A, right? So then also you can easily show B2y is 0, because if you take this one and this one, what happens? If you take this product, you can see B2y, if I take A1 and B2, so now we show this is, you can easily take, there are 4 equations, right? If you do that one, you will easily find your B2x also, 2 pi over A. B2y, yeah, is 2 pi over A. So that means you will find your 2 vectors are only these 2. There are 4 equations here, right? If you do that one, you will get the idea. Is that clear? So if I have this real space, then my reciprocal space, I have B1, B2, but B1 is given by simply 2 pi over A, B2 also given by 2 pi over A. So that means in the reciprocal space, I can write all the coordinates. So this means really G10. Here, this is exactly, this from here to here, this is simply G10. What is this one? G01 in the reciprocals. What is this one? G11. Right, this is in the reciprocal space. Now if you take this one should be perpendicular to this plane. That's correct, right? So how about B2? This is G01. That should be perpendicular to 01 plane. How about this one, G11? That should be perpendicular to this plane. That's correct, right? If I draw like this, you can see G11 is perpendicular to that plane. Is that clear? So you can see how all this, if you take this one, this is G21. So that G21 means you have 2 times B1 plus 1 times B2, right? So also G21 should be perpendicular to G21 plane. So this is, you can see G21 here, this is, they are perpendicular. Is that clear? This is a very important thing to remember. So now I put these two together, then you can see everything, right? Real space and the reciprocal space. Also sometimes when I talk about these things, I might sometimes neglect this 2 pi term. So B1 is really 2 pi over A, right? Sometimes I might write 1 over A, like this, 2 pi sometimes people. Ideally it is 2 pi. That's basically normalized. Now everybody is familiar with reciprocal space and how G vector is related to the plane. So another example here, look at this one. This is my real space. So how do you get the reciprocal space? This is little tricky because how do I write? I will give a homework for you to practice that one. How do I write A1? That's easy, right? A1 is basically A times unit vector, right? A1 is A times unit vector. How do you write A2? A2 is this vector plus this vector, right? So that is actually, if you draw this one, this angle is 60. right? So this is A, that means this is A sine 60, that is A square root of 302. This is A cos 60, that is A by 2. That means this vector is really this vector plus this vector. That means I can write A2 as, this is positive, this is negative, right? Negative A by 2 times X, here this, plus A square root of 3 by 2 times Y. That's the two vectors, right? Because these are, okay, get this one. Now if we want to calculate my, so this is this one plus 0 times Y, right? So now if you want to get B vectors, basically you can write B1 as, say, B1x times x, B1y times y, then B2, these are the ones I need to calculate, right? B2x times x, B2y times y. So we have 4 equations. What are 4 equations? Kronecker delta equations, right? A1, B1 equals A2, B2 equals 2 pi. The other one A1, B1, sorry, A1, B2, A2, B2, B1, all this 0, right? 4 equations. From there you can easily calculate this one. If you do that one, you can easily find your B2, this value is 0. Just take maybe this, if you take, yeah, this, if you take dot product of this one, what happens? A dot B2, A times B2x, A times B2x plus 0 equals 0, right? So that means B2x is 0. That means you have only B2y. That's why you have B2 is just only y direction. But B, if you calculate B1, that one has both B1x and B1y. Well, that's why you have. It's very easy to do. It's simple calculation. Right? Is that clear for everyone? Yeah. So now if I take this real space, if I calculate my reciprocal space, now I know the 2 vectors, then I can generate all the G vectors, right? So you can see the shape is completely different. For example, if you do the graphene, if you have a graphene real space like this, if you take a reciprocal space, this is rotated by 90 degrees. So we'll do these examples later. So now for this one again, I will draw the G vector. This is my origin. This is my 1, 0, 0, 1, 1, 1, 2, 1 like that. So then if you look at all the planes, you can see all these. So G21 will be perpendicular to that 2, 1 plane right here. Like that, everything. Please do this yourself, then you'll get that view. So from here to here, you have to do little calculation, right? That's what I'm telling. So this is some way to do that, but don't use this one directly if you use the 2-dimensional. Use simply that Kronecker delta relationship. So actually you can do this one by assuming your third vector is normal to that 2-dimensional plane, you get the same answer. Okay. So now let's do a very simple situation, reciprocal space in 3 dimension. So take the simple cubic lattice. We know how to write A1, A2, A3. This is correct, right? X. So now if I want to use this relationship, right? First I need to calculate what is my this denominator. Everybody know how to do this one? It's a triple product, right? That's basically a determinant. So how do you do that? The denominator, that is A1 dot A2 cross A3. How do you do that one? This basically calculate the determinants. What is A1? A times X. That means you have A, 0, 0. Then A2 is only white one. That means 0, A, 0. A3 means 0, 0, A. If you calculate this determinant, you get only a cube, right? That's your this one. What is this one really? That's the square of the volume of that cube. Also, we know this is the primitive cell. So, right, this is the smallest unit cell. So now if you want to calculate this real space, in the reciprocal space, if I want to calculate B1, B2, B3, just simply calculate this one. How do you do this one? A2, so this you have 2 pi here, then bottom you have a cube, right? This one is a cube. Then here what we have? A2 cross A3. A2 cross A3, that means you have A times A1, A square, times what is Y cross C? Y cross C becomes X, right? This is a vector product, X, Y, C. X, Y, C. So if you have right hand rule, right? X to Y, so this will give you X direction. So that means you have, so what you have, A square, this cancel, you get 2 pi over A times in this direction. Yeah, 2 pi over, like that, you can calculate everything. That's easy for simple cubic. If you take a face centered, okay, yeah, let's do that one also before we go further. I'll finish that one and come back. If you want to do the face centered cubic, face centered, remember, this cell is not a primitive cell, that's a conventional cell. Why is that? You have 2 lattice points, right? Primitive cell means you need to have only 1 unit cell. That's why we make this new primitive cell. We just connect to the center of each face. Face centered means you have atom at each face, right? So you just take center of this one, center of this one, center of that one. So now you can write the A1. If you consider A1, how do you write the vector? So this is actually in the 0th X, right? So that means you have only, this is right at the center of this face. That means half times Y, half times C, right? Because right at the center, X direction is 0, right? So if you take this face, that is A3, basically it is in the 0th C direction, right? So C part is 0, you have half of this one. If you take this one, that is 0, Y, right? So you have no 0. It is clear, right? All the now you know A1, A2, A3. So if you connect this one, you get the primitive unit cell. That's the smallest volume, right? This is not the primitive cell, remember? Because that has 2 points, right? If you connect this one, the polyhedra you are getting is the unit cell. Now we want to calculate B1, B2, B3, right? So we know how to do that one. So first we have to calculate the determinant. What do you get? For the denominator, you have A1 is A over 2, Y, you have A over, 0, A over 2, A over 2. So then this one you have A over 2, 0, A over 2, right? This one has A over 2, A over 2, A over 2, A over 2, 0. Now if you calculate this one, if you take this one, this is 0, then usually plus minus, right? Then you have A over 2. If you take this one, you get only negative A squared over 4, right? 0 minus A squared over 4. Then you have plus A over 2 times, then you have A over 2 squared, right? So what you get is, oh yeah, the whole thing squared, right? Yeah. So you get A squared over 8 plus A squared over 8, that is basically A squared over 4, right? So that's, oh sorry, A cube, yeah. So A squared times A is A cube here. Is that clear? This is A squared, right? There's another A, then A cube, then 1 over 8, this becomes a cube over 4. Please, you can do this calculation. So then we know how to take the cross product. If you calculate B1, A2 cross A3, if you calculate this one, we know how to get the cross product. Then you have, so if I write this one, 2 pi times, bottom we have A cube over 4. Then the numerator we have A2 cross A3. You have A squared over 4, right? When you multiply these two. So then if you take this one, x cross x is 0. X cross y means c, right? You get c. Then we are doing A1. Then we have, first we took this one, right? Then we have c times x is y, right? C negative.
Yeah.
Negative y, right? So this is 0.
We're doing A1 and A3.
Oh, we are doing A1, yeah, sorry. Yeah, A1, A3. So this, yeah, you get the idea, right? So you can, yeah, so this positive, negative, everything, yeah. So please remember this cyclic. X, y means C, C, y, y. If you go XC, that is minus y, right? You have to remember. You get the idea. You can easily calculate this one, right? So then you can see this A squared. So here, A squared, here, one of them cancel, then you get all these numbers, correct? So anybody remember, if you see this kind of thing, what is this structure? This is actually body-centered. Remember, if you have body-centered one, that is the real space coordinate, right? Because you have, if you, from here, that's actually center of each. This is the primitive cell for the body-centered, because the one unit is not a primitive cell, right? You have to connect to the center of each one. That's why we get this one. So compare this one with what we got in the previous one. It's the same relationship, right? So what I calculated here. So that means the real space FCC lattice become reciprocal space body-centered one. So vice versa. If you take the body-centered real space, please do yourself this one. You will find you will get actually this only one thing missing. That is for the face-centered one, right? So that's very important. Like BCC real space becomes FCC. FCC real space become BCC in the reciprocal space. I think it's good to practice these calculations. Very simple, right? It's nothing. Okay, now I want to go back and do these things that we were talking about. Okay. Now, if you remember, we talked about these planes, right? Suppose my HKL plane. So actually this small looks like 100 kind of plane, right? But just a general HKL plane. So then each plane, even this one, right? The plane has some given separation, right? We call the space between two planes. So separation of planes. So suppose that distance is d for that given plane HKL. So we can easily prove one thing we already know. This we already talked about, right? What does this mean? GHKL vector is always normal to the HKL plane, right? So this is some vector in the reciprocal space, but that vector is always normal to this one. But also we can show the distance between these two planes is 2 pi over that magnitude of that GHKL vector. So if we want this HKL, this is nothing but 2 pi divided by, that's a vector, right? GHKL, the magnitude of that vector, 2 pi over that vector is simply the space in between the two. This is what we use for next chapter, diffraction, electron diffraction, X-ray diffraction. These are the two things we are using. This probably in diffraction, this is the most useful two relationships. First thing is your G vector is normal. Next one is the space in between two planes given by 2 pi over that vector magnitude. Your GHKL is a vector, right? So remember GHKL is nothing but H times B1, K times B2, L times B3, right? That's the vector. So then magnitude is basically, you have to take the magnitude. So I'll show you later how to do that one. Okay, so first let's prove these two relationships. That's very straightforward to prove that one. So first one, to show this GHKL is normal to this plane. Suppose I have these 3 vectors, right? So going from, say, if I write my that R, M, N, O, remember any translation vector is given by M times A1, N times A2, plus O times A3, like that, right? So that means if I draw from some origin, we have this points given by MA1, whatever those 3 points. So I'm talking about a vector GHKL will be normal to the plane through points that has, so you have some plane. Actually, I'm talking about something like this. Just, yeah, let me show you. Just look at, this is what I'm talking about. If I have some plane like this, the G vector is normal to that plane. So, but we know this plane is passing through this. Actually, it's 1 okay, remember that's why we take the reciprocal to get the real index, right? So these are passing through 1 over H, 1 over L, and 1 over K, right? So that means actually, if you consider these 3 vectors, actually we have GHKL, we can show this is normal to some plane that is passing through this MA1, MNA2, OA3. We can find 3 points so connected by this plane. That means I have some line here. What is that line? MA1 minus OA3, right? Because this measured from here to here. What is this vector? Basically OA3 minus N1. Same way I can write this vector Na2 minus Ma1. So this vector I can write as Na2 minus OA3, right? So can you see this? These 3 vectors are lines on that plane, right? So now if the GHKL is normal to that plane, what is the definition of a normal? Typically, if the normal is perpendicular to 2 intersecting lines, that is normal to that plane. That means it's normal to any line on that plane, right? That's the definition of a normal. So that means I can say these are vectors now on the plane, right? So each one is perpendicular to that vector. That means if you take the dot product of that line with the normal, that should be 0, right? So that's what I'm writing here. This is a line on that plane. Is that clear? So this is another line. If you do this one, what do you get? GHKL I can write as HKL, this expression, right? GHKL is basically GHKL H B1 K B2 L B3, right? So now I want to take dot product with MA1 minus NA2. If you take dot product, what do you have here? A1, B1 is 2 pi, right? So you have only H times M. Then these are all 0. Then here you have minus K times N. Everything else is 0, right? So this should be basically 0 because that's, you have 2 pi term, that's cancelled, right? You know why this is 0, right? Because they are normal. So if you do that one, you get this equation. Then I can write M as simply K over M is Kn over H. Kn over H. I'll write Kn as some constant A over H. M is A over H, right? Or I can write N as Kn is A. That means Kn is A means N is A over K, right? Same thing I can write if you take this one, you can easily write O equals Mn O also equals A over L. You can see the three. Pretty straightforward, right? What does this mean? If I take, say, A is 1, so this is basically 1 over H, 1 over K, 1 over L. So that's exactly that where they intersect, right? Because when you take the Miller indices, we take the inverse of that one, right? So that proves you this GHK vector is normal to the HK plane. Is it clear for everybody? This has to be inverse, right? Because when you do the plane, you take the inverse of that one. Okay, so now that proves you the concept of the GHK vector is normal to the HK plane. Now, yeah, that's basically how we prove that one. So now how do you show this? The distance is 2 pi over GHK. This is the most important thing for the crystallography. That's also very simple. Just imagine in the real space, if I have a plane, suppose this is my HKL plane, right? So that means what? This is cut in actually at 1 over H, right? So this is like 1 over K, sorry, H, yeah, C direction. So just draw in the 2 dimension like this one. I want to find from origin, maybe we have other plane here, right? So if I want to find the distance between these 2 planes here, so how do you calculate that one? Anybody remember how do you find the perpendicular distance from a plane? So anything, if you have, suppose this is vector R, how do you find? That's what we need, right? What you have to do is take the dot product of this one with the unit vector in that direction, right? That's the, so this distance is basically R dot unit vector in that direction. So that will give you the projection, right? R dot N is what really? R, suppose this is theta, R times N is 1 times cosine theta. What is R cosine theta? It's distance, right? That's what we need. So if you want to find that perpendicular distance, only thing you have to do is, this is my any R, suppose any general R here. So then this distance will be that R, you have to multiply by the unit vector. What is that unit vector? It's the direction of GHK. So that means unit vector is vector divided by its magnitude, right? So then you have this R, but for simplicity we will take that point as this point, right? If you take this as the point, what is that point? That's simply 1 over H in the direction of X or A direction, right? So this is 1 over H because instead of any general point, I just took special point here. So if you do that one, you get this relationship 1 over h. So x also I can write in terms of the unit vector. Then also GHKL is, actually this is ideal, this should be B1. Sorry about this one. So GHKL I can write as h times B1 k times B2 like that. So but if you take the dot product, only the this one times your the h terms, right? So h and h cancel, you get only 2 pi terms. So please replace this one in B1. Because sometimes people write this different notation. Real space they write A1, A2, A3, then reciprocal space sometimes they write A2, A3. But we stick with B1, B2, B3, right? Please replace this one with B1. I will do that change. So we know this one basically A1 dot B1 means 2 pi. So that proves you. Is that clear? So that's basically these are the two important equations to remember. Yeah. Please remember this one. This vector is normal to the HKL plane. This one, can you see something wrong here? GHKL vector is, what is missing there? It should be 2 pi, right? Like I said, sometimes 2 pi I might, lot of books also I think they neglect that 2 pi. Ideally this should be 2 pi over DHKL. If you know the your reciprocal lattice vector, that magnitude of that vector is basically the inverse of your spacing. Okay, so let's now, how do you calculate this vector directly? So then we will stop here. Yeah, okay, yeah, in good times. Now suppose if I have lattice. So now if I, so this some, say even simple cubic lattice. So if I take this plane here, right, so central plane like this one, you can see how this one is here, right? So now I want to find the distance between two parallel planes, right? So now here you have only one plane, right? What do I have to do is put another box, right? From all around this one I can put 3 more boxes, right? If you do that one, I will see like this. This is the box I am showing here, A and A, right? If you put another 4 boxes, so it looks like this. And now you can see this is one plane, this is the other plane like that, right? So now this is what we want to calculate, right? The distance between the 2 planes. So how do we calculate that one? That's pretty straightforward, right? We know this is A, so then this is 45 degrees. So then what is this distance? D1 right here. So I can easily write D1 1 0. So everybody agree this is the plane of 1 1 0, right? So then this distance, this is A, this is 45 degrees, so this is A cosine 45, right? A cosine, A times cosine 45 means 1 over square root of 2, right? A over square root of 2, that is D11, yeah, so that's directly you can calculate, but you don't want to do this geometry, right? Typically, if you give you the crystal structure, you should be able to directly calculate that distance. How do you do that? It's basically do some vector relationship. Here we know how to write your G. What we have to calculate is, if you calculate G110, then this one is 2 pi over that G vector magnitude, right? Usually you can use this relationship. D110 means 2 pi divided by that G110 vector, the magnitude, right? That's all we have to count. So how do you calculate this one? G110 means what? H. H is 1 here, right? B1 plus K B2 plus L B3 like this. So then this I can write as, I just write as a general one, H times. So if this is a simple cubic, B1 is 2 pi over A, right? Yeah. So if it is simple cubic, I can write this one as B1 is 2 pi over A times A1, right? Yeah. A1 vector. So X, yeah, in the unit vector. So here plus K times 2 pi over A times unit vector plus L times 2 pi over A times C vector. So that means I can write my G110 vector, just any general vector, HKL, but this only for simple cubic because this is different if it is different one, right? This is only for simple cubic. I write as 2 pi over A times HX plus KY plus LC, right? So now we know how to calculate the unit vector of this one. HKL. What is the unit vector? The same 2 pi over A. Then you have to take the square of these three and take the square root, right? It basically square root of H squared plus K squared plus L squared. So that's the answer. But in our case, if it is 110, that means this is basically, so H is 1, K is 1, this is 0, right? So that means basically 2 pi over A times square root of 2. You get the same answer, right? But one thing I think a lot of people make this mistake, you can do this one only when you have unit vectors here, right? So if you have something like this, suppose your A vector is some m times A1, n times A2 plus O times A3. If you want to calculate A, you cannot take this one. This has to be unit vector, right? So I have seen a lot of people make mistakes. So only first you have to write everything in terms of x, y, z, then take that square root. I give one example for you to do that one in the homework problem. So this is the one, right? DHKL is given by this A. Yeah, you can see here 2 pi. This equals, yeah, here this equals 2 pi over this one, right? 2 pi over D1 equals 0. That means 2 pi cancel. Your D10 is A divided by this one. Is that clear for you? Yeah. So then very last thing, then we'll finish here. Yeah, we did this one. So last thing, remember we talk about the Wigner-sized cells. Wigner-sized cells means in the real space we take the nearest neighbors and we just bisect the numbers, right? Now we are going to do the same thing for the reciprocal space. So now suppose this is my real space, so we know how to draw the Wigner-sized cell, right? Basically cut this one, this is my Wigner-sized cell. That's a primitive cell because it has only one unit cell. So now if I go from here to here, I get to the reciprocal space. That means these are A1, A2, here we are talking about B1, B2, right? This is the reciprocal space. So now if I do that same thing, Wigner-sized cell, if I do in the reciprocal space, same thing, right? We just take this one and cut here. So this is called the reciprocal space. Wigner-site cell that has a special name called the Brillouin zone. This is called the Brillouin zone. So Brillouin zone means reciprocal space Wigner-site cell. So if, for example, if I take this hexagonal real space, so again we know how to draw the because here you have all these nearest neighbors, right? You have to bisect all of these, you get hexagon, right, as the Wigner-site cell. If you go from here to here in the reciprocal space, again you get similar hexagonal, you can easily show that. Again, if you calculate your Wigner-site cell, again you can see you have all these 6 nearest neighbors, right? You just bisect. This is your the Wigner-site cell, that's called the first Brillouin zone. So then you can do the second Brillouin zone. How do you do that? Go to the next nearest neighbor. For example, these are the nearest neighbors, right? What is the next nearest neighbor? This one. Then you bisect that one. So go to the this one, like that. Then you get the next nearest neighbor. If you want the third Brillouin zone, then you have to go to the third nearest neighbor. So we'll do one example homework, then you know how to draw all the Brillouin zones for. So Brillouin zone means Wigner-site cell in the reciprocal space, that's all. Because like I said, you are going to do all the calculations in the reciprocal space, right? Because that's easier, because you represent all the parallel planes with only one point. So now when you do the calculations, that also makes it easy. You don't have to do anything beyond the first Brillouin zone. So anything beyond first Brillouin zone, we call the zone folding. We can fold it back to the first Brillouin zone. So you only have to worry about what is happening within the first Brillouin zone. Then you can fold it back to first Brillouin zone. That's how theories make things simpler, right? Otherwise, it's too much calculations to do. Okay, so I think now we have everything to start talking about diffraction. Here are the Brillouin zones in other dimensions. For example, if I take face-centered cubic, we know the reciprocal space is BCC, right? If I take this one, we already showed you how to make the Wigner-site cell. So for this one, what you do is you just bisect all nearest neighbors. Then it becomes, this is your first Brillouin, not the Brillouin zone. First, that the primitive cell. For the primitive cell of this BCC. But if I go to the reciprocal space, if you take the Wigner-site cell again, you just intercept all the points, so then you get this. What is this one? This is the first Brillouin zone of the FCC structure. FCC structure has this special the Brillouin zone. So this one, if you have this Brillouin zone, this is very important. Maybe later we'll talk about that one. We define these several the symmetry points and symmetry directions. The very center, most symmetric point, the very center we call the gamma point. So later you will find most of the calculations we do at the zone center. Then we find this one special point. You can see this hexagon here, right? Center of that hexagon is called L point. So then there are this another X point, that's the center of this rectangle here. So then there are 2 points, this KWU. So these are some kind of symmetry points. So if you go along this gamma point to L, we call this direction like this gamma direction. If you go from here to here, that's called the delta direction. Going from here to here, we call it the sigma direction. So sometimes you need to know this one if you want to read the band diagrams. But better to have some idea. It's easy to remember gamma points, right? So also X point also some, also L point, L, X are centers of surfaces. Gamma is very center, X and L points are center of faces. Basically one on the hexagonal, one on the rectangular faces. Others are like at the edges. So we'll talk about that one later. Okay, that's all I have to talk about.